Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. Last time we dealt with collisions between ABs, OBBs, and a number of other things that probably would have made Dr. Seuss proud had he had a penchant for computer science. And today, I'm going to finish off collisions with ABs in the form of detecting collisions between ABs and triangles. We're going to have ABs and planes. And we're also going to be doing like ray casting into ABs, into rather OBBs, and line casting and detecting collisions between OBBs and like rays and that sort of thing. So let's see. I think, collapse a number of these collision detection methods over here because they're just taking up space on screen, and I don't really want that right now. I'm going to start off with checking for collisions between ABs and planes. This is going to be a little bit, this isn't going to be that many lines of code. I don't know if I want to call it simple, because it's not simple in the way that checking for an intersection between a shape and a sphere is, although to be fair, not many things are. But what we need to do to check for a collision between a plane and an OBB is going to be basically to make sure that all 8 vertices of an OBB are on the same side of the plane. And you can do that in a couple ways. You can totally just bar these set of 8 vertices of the OBB, and you can use the dot product against the plane's normal to make sure that they're all on the same side of the plane with like respect to the plane's origin and distance from the origin and that sort of thing. But that's going to be a little bit ugly and expensive, and I don't want to do it. So instead, I'm going to let's say project the axis of orientation for the OBB against the normal of the plane, and subtract the plane's distance from the origin. Got to remember to do that, and check to see if that projected distance is less than the distance from the OBB to the plane. So we can start by saying, I'm going to call it p length, L-E-N-G-T-H. I should just call it p len because I know I'm going to mess up typing that and spelling it a bunch of times. This is going to be a somewhat elaborate expression, which is going to be self.size.x multiplied by the absolute value of self.plane.normal, self.plane.normal, the incoming plane's normal, dot product against self.orientation.x, double close parentheses, and we're going to add that to self.size.y
multiplied by the absolute value of plane.normal.self.orientation.y, and we're going to add that to self.size.z multiplied by plane's normal dot product against the z-axis of orientation, as I mentioned.
And the distance that we're going to compare that to is going to be the plane dot normal dot against the self dot position. So we're going to project the position of the OBB onto the normal of the plane. So we're going to get the length of that vector in the direction of the normal, and we're going to subtract the plane dot distance because if the plane originates at somewhere other than the world origin, then you'd like to know.
Hey.
And lastly, we can return the absolute value of the distance as less than the p length, so the projected length, and that should be all that we need for OBBs versus planes. If I were to run the game, and if I were to bring up an OBB, and if I were to bring up a, what is it? The B key is going to be a plane. We could raise and lower the OBB above and below the surface of the plane, and we have the shapes overlap notification disappearing at the appropriate times. If I were to move you around as far as I wanted, we could have the like, it doesn't matter how far we go, planes are infinite, we are going to have a collision detected no matter where we are, as long as like we're not above or below it, like this. If I were to turn this around, numpad 4 is going to be a plane, the O key on the keyboard is going to be an OBB, and if I were to move the plane around instead, because that's I think it would what do I do? Okay, so the left and right arrow keys to rotate. I think it would sell the fact that we're doing this intersection a little bit better if I were to rotate the plane as well. I don't have like a great test. Like, I don't have a great test system for planes. Can I Like, it doesn't help that it's hard to see exactly where they are because they're not, like, lit, but we can pass the plane through the OB as well. We can detect collision. We can rotate it. We can rotate the plane, and we can detect collisions. All right. Like, the plane collision detection code that I've written for all of these objects isn't, like, complicated, but testing it is kind of a pain because, like, as I said, I'm not super 100% happy with my, like, test code for the planes. But anyway, that's OB versus plane. That took us, what? A couple of minutes. Alright, next, we're going to do OB versus triangle. This is going to be another separated axis theorem, so I suppose I could get started by just copying and pasting the OB versus AB code. And we could just, we could configure the axes of separation as appropriate. The first thing I'm going to do is I'm going to get the 3 vectors representing the edges of the triangle. So I'm going to say var edges is going to be equal to triangle.b.sub, triangle.a, and then triangle.c.sub, triangle.b, and then triangle.a.sub, triangle.c, like this. Now, these 3 edge vectors aren't going to be axes of separation on their own, but I will include the normal of the triangle. Call triangle. Does that have a normal vector, or do I have to calculate that myself? Is there like a get normal method? I don't remember if I implemented like a get normal. There is a get normal method. All right. So we're gonna have a get normal method for the triangle, and one of the potential axes of separation is going to be that. So we can say triangle.getNormal like this, and that's just going to be like the cross product of 2 of the edges against each other. If your triangle has 0 area, then that is going to pose a bit of a problem. You're going to have a normal vector that's like undefined, like 0, but we're going to assume that you don't have that when you define these triangles. And we're going to need 9 more potential axes of separation. There's going to be 13 in total, which is a little bit less than the 15 of the call OB versus things, rather. And those 3 are going to be the 3 edges of the triangle crossed against the 3 axes of the OB's orientation matrix. So again, we can do a little for loop. We can array push onto the axis array the 3 axes of orientation crossed against the 3 edges. And instead of having a doubly nested loop here, we're just going to have, well, I guess we will have a doubly nested loop, but it'll just be each of these 3 axes of orientation versus each of these 3 edges. And we're going to push that onto the array. There will be 13 in total. So we can iterate over that number. And I'm going to need to check the interval of self and the triangle. I'm going to, again, have to make sure that I'm checking against a variable name that exists if I don't want the game to crash. All right. So this should give us OB versus triangle. Let's see, that's going to be an OB. Which key is triangle? There's too many shapes. I'm keeping them straight is hard. So right off the bat, we have an overlap test between the triangle and the OB. If I were to move you out, all right, good. You stop colliding approximately there and also there on the other side. If I were to move you in another direction, up, down, whatever, intersection starts. If I were to look on the other side of the triangle, you could see that we barely see part of the OB, like poking its nose through. And on this side, same thing. And that is our OB versus triangle. Okay. The separated axis theorem really does make a lot of things easier. If you have 2 shapes that aren't that are defined by faces like a triangle or an OB or something like that, I'm still a little annoyed that I couldn't figure out how to get rid of all the edge cases in triangle versus triangle using the separated axis theorem. I'm sure there's a way, and I just didn't find it in time. All right, well, let's not dwell on that. So that's going to be implemented OB versus triangle. And what else do I need to do? Okay. OB versus Ray. This is gonna suck. I also am not completely sure what the best way to explain this is. Ray versus ob. But we'll get it done one way or the other. I am at about 16 minutes on my recording time. I'm curious as to exactly how long it's going to take for me to not only explain this, but also probably to explain it like 2 or 3 times and like figure out which one I like best and go with that one. Anyway, check ray. We're going to have a ray and a hit info that's passed into this method as a parameter. Let's see. The first thing I think I'm going to want to do is I'm going to want to say size array equals self.size.as linear array. Not going to be, at least not right now, and I don't think I'll need it. I'm not going to be getting the components of the orientation as a vector array. I should be okay without having to do that. Let's start by saying var_dir is going to be self.position.subtract ray.origin. So this is going to be the direction from the ray to the position of the ob. Next, I'm going to create an array of size 3. This is going to be direction dots, and that is going to be self.orientation.x.dot producted against the ray's direction, and we're going to be doing the same 3 for our other 3 axes of orientation, x, y, and z. And next, I think I'm going to want an array that's like position dots, and that's going to be self.orientation.dot against the like the vector from the ray's position to the ob's position. So that's just going to be dir like this. Next, I'm going to create, and this is going to look vaguely similar to the abs check ray method. Where are we? This is going to look vaguely similar to the abs check ray method. I'm going to create, instead of a bunch of variables called like t1, t2, t3, and so on and so forth. Wow, did I really not use an array there and iterate over the array? That would have made like my life a lot easier. I'm not sure why I wrote everything out the long way like that. But I'm going to create a temporary variable called t, and that's going to contain information of the ray passing through each of the 6 sides of the ob. The way that Gabor Zauer describes it, and the way that some others have described it in Game Physics Cookbook and elsewhere, is that if you unwrap the rectangular prism that is either an axis line bounding box or an oriented bounding box, if you imagine that you have a cube made out of paper, and then you unfold that cube into just like a flat sheet, you could think about a ray intersection as basically unfolding your ab or unfolding your ob in that way, and then testing to see if a line drawn like on a piece of paper intersects any of those slabs. But I have elected to not use that metaphor because I don't think that the code I'm writing really looks like unfolding a cube in that way, and I feel like that would add more confusion. Let's go back to call ab check ray. T, as I said, is going to be an array create. It's going to be initialized to a size of 6, and it's just going to have values initialized to 0. Normally I wouldn't like initialize values like that to 0, except that Feather likes to yell at me if I don't initialize my arrays to a value. So to keep GameMaker's like IntelliSense happy, I'm gonna initialize that to 0. Next, I'm going to iterate over var I equals 0, I is less than 3, I plus plus. Iterate over each of the like the direction dot product values over here. First, if the direction dot index that's gonna have to be index I equals 0. Then this is going to be a bit of a special case. This is going to be the ray being parallel to the orientation dot producted against the ray. So if this is going to be 0, then the ray is going to be like perpendicular to this vector and parallel to one of the sides. And that brings up a little bit of an early out that we can do. So if the ray is not like exactly inside the face that it's parallel to. So if the ray doesn't like spear straight through it, spear straight through the face, then we can know already that the ray does not intersect the ob. So we're going to figure that out by saying if double open parentheses negative position dots index I minus the size array index I is, and I'm going to need to close parentheses there, is greater than 0, or the negative position dots index I plus the size array index I close parentheses is less than 0, then that means that the array is either way in front of one of the faces that it's parallel to, or it's behind the ob on the other side, on the opposite side, and we can return false. Otherwise, we are going to want to set direction dots index I equal to some very small number, so I'm going to say 0, 0, 0, 1, so 1 in 1/10,000th or so, because we are going to have to divide a term by this value, and we don't want to divide by 0, because that would throw an unnecessary wrinkle in things. I need this to be up here after this early out, checking if the array is in front of or behind the ob like this. Next, I'm going to say t index I times 2 equals, and I'll explain the plus 2 in a minute, equals position dots index I plus size array index I, and this is all going to be divided by direction dots index I, and t index I times 2 plus 1 is going to be position dots index I minus the size array index I divided by direction dots index I. And just so that these two lines are coded at the same length, because that makes me happy, let's say t index I times 2 plus 0. So the t array, the temporary array, I wish I had a better name for that, now that I'm actually trying to say it out loud, now that I'm trying to make a video on it. But there are going to be 6 indices in this array, 2 for each of the orientation vectors x, y, and z, and that's going to be one index in the array for like the front of each vector, and another index in the array for what's the vector going in the opposite direction at the back of the ob, because remember, each of the components of the orientation array are an axis of rotation, which is a little bit different from the degrees of rotation on any given axis that a lot of people intuitively think of rotations about in space, but it's basically the nice alternative to quaternions, but we're not going to go there. So, outside of this for loop, we can do, again, something that looks vaguely similar to raycast versus an ab, and that is going to be, I'm going to say t min is going to be the maximum of a couple of values. That is going to be the min of t index 0, t index 1, the minimum of t index 2, t index 3. So this is going to be the front and back results of the raycast against each of the axes, and the minimum of t index for t index 5. And we're also going to want a t max, which is going to be the opposite min-max function, so it's going to be the minimum of the maximum of these 3 pairs of values. Next, if t max is less than 0, return false. So the array is not the array is pointed away from the ob. And also, if t min is greater than t max, return false. Otherwise, we are going to return true, and we are going to figure out exactly where the raycast hit information belongs. So again, this is pretty similar to the raycast versus ab. This is checking to see if the raycast is pointed away from the shape in one direction or in the other direction. I guess you could think of that as the forward direction or the backwards direction, but it seems like a weird way to put it for me. Anyway, so we need to start figuring out exactly where the ray hits. So that's going to be var t result. This is going to be one of two things. If t min is less than 0, then t result is going to be equal to t max. Otherwise, t result is going to be equal to t min. This is a nice conditional operator, makes if else's a little bit more neat and tidy. And var t normal, I'm going to initialize this to a new vector 3 populated by zeros. And I'm sorry, this is going to be done only if the hit info parameter has been defined, because if you're doing a raycast and you're not supplying a reference to a hit info struct, which is going to collect information on the like the point of contact and the normal of contact and that sort of thing, then it's a it's work that you don't need to be doing, really. And also, regardless of whether or not we're populating the hit info struct, we need to return true. Okay, so now we need to figure out the contact point for one. We can say our contact point is going to be equal to ray.origin.add ray.direction.multiply t result. So that's going to be the distance. T result is going to be the distance from the ray's origin to the point of contact. Again, that's pretty much the same thing as we've got in the... Oh, I didn't use the conditional operator here. In add versus ray? It's weird. Also, I'm not checking to see if hit info has been, like, defined. Has been passed into the method, apparently. Which I think is generally a good thing to do. Because sometimes you just want yes or no on a raycast and you don't care about all this stuff, but... Alright, pass me. Whatever. Let's see. I'm going to define an array. I'm going to call this possible... normals, and this is going to be an array of 6 values for each of the normals of each of the 6 faces that have been like defined up here. The possible normals are going to be simply self.orientation.x, self.orientation.x, but backwards, so that's going to be multiplied by -1, and it's going to be the same for y and z. So each of the faces of the OB are going to have normals that are just the axis of orientation, and the one on the opposite side is going to be the negative axis of orientation. And to figure out exactly what the surface normal of the point of contact was, we're going to loop over the array of possible normals. We're going to figure out exactly which face the ray hit, and we're going to do that by comparing t result to like the t value of arrays over here. This stores the distance from the array to that, from the ray that you're checking, the ray that you're casting to the surface. And if each of the, if the distance to the point of contact is equal to the distance to the face, then that's the face that we hit. We can use that normal information. So that's going to be for var I equals 0, I is less than 6, I plus plus. If t result is going to equal t index I, then t normal is going to be normals, possible normals index, plurals, possible normals index I. And in my notes, I went out of my way to normalize this vector, although since we're not dealing with scaling in any of these shapes, each of these normals should have a unit length of 1 anyway. If they didn't, that would cause some consequences when it comes to some of the other collision checks, but I guess I'll ignore that for now. We will not be dealing with scaling. 3D collision systems often avoid scaling.
Hey.
Anyway. So we have the distance to the point of contact, we have the shape that we're contacting, which is just ourselves, we have the point of contact, and we have the normal. So we can say hit info.update with the t result. The shape is going to be ourselves, so that's the shape that we hit. The point of contact is going to be contact points, and the normal is going to be t normal. In hindsight, I should have named this something like contact normal instead. Let's do that. Most of this is just copied from my, and I can call this like contact distance or something too. It's probably more helpful to do that. Most of this is just like an updated version of the abs check ray method. Once again, you can see a lot of similarities here, although I am not using a for loop, which would have made my life a little nicer. Which was in turn mostly just borrowed from Game Physics Cookbook, and that used some less than helpful names for some of these variables. But that is a raycast into an OB. If I were to run the game is either going to crash horribly, or we're going to detect collisions. T result, that needs to be t contact distance, like that. So we're going to run it again without any misshapen variables, and we can get the the raycast, so we can see the point of contact in the form of the ball that is appearing on the OB. We can see the direction in the form of the like the secondary ball that's coming out of the surface in that direction. All right, so raycast and OBBs. That was actually not as bad as I thought it was going to be. Also, to answer my previous question, that took about 19 minutes of real time. We'll see what that gets cut down to in editing. All right. If I have two call OBBs, we're also going to be raycasting against both of them, and it looks really funny actually when like I'm raycasting into two shapes that have almost the same point of contact, like this, where they're on top of each other. Looks like some like mutant chemistry molecule example. Anyway, let's get out of there. We can implemented OB and raycast. And I think the last check that we have to do is for OBBs and lines. And as we so often do, we're going to just do this by casting a ray into the OB, and we're going to check if the well, one, if there is a point of contact, if the ray hits the if the ray hits the OB at all, and then if it does, we're going to check to see if that point of contact is less than the distance of the line segment. And because I am lazy, and because it's going to be the same anyway, we can just borrow that from the AB shape. It's kind of nice sometimes how similar these two are, although it's also somewhat infuriating in that some assumptions that you can make about ABs you can't make about OBBs. These 8 lines of code send their regards. But we're gonna basically cast a ray into the shape, and as I said, if the hit info.distance is less than the line's length, then we're gonna return true or false. Okay. The line shapes are also kind of suck as far as my my 3D shape tests go. What is line? That is gonna be the N key on the keyboard. If I were to move the OB around, you can see that we have intersections between the line and the OB. Okay. Well, that's going to be it for, I think, the current set of a 3D shape intersections that I have. That one was... I said that planes and shapes were generally pretty easy, but honestly, lines and shapes are probably the easiest, because lines are really all just doing this. But no matter. We're going to say implemented OB and lines, and I think that's going to be it for this video. So, we have fully implemented collisions between oriented bounding boxes and all of the other shapes that are currently in the system. The only thing left is capsules, and honestly, capsules are nice for humanoid-shaped objects, but if you did not want to include them, they're probably, I would say, unfortunately, I'm sorry, capsules, you're a nice geometric shape, but they're probably the most ignorable shape in this entire system that I'm going to be doing here. Points aren't used directly in a lot of 3D collision systems, but they're a nice starting point for things like spheres and stuff. Spheres are nice for a lot of things that are approximately spherical in nature. OBBs are useful for like a lot of solid objects, a lot of like inorganic solid objects, like crates and barrels and treasure chests and that sort of thing. ABs, even if you don't use a lot of ABs in your collision world, if you want to rotate an object, you would be using an OB anyway. ABs are really good for things like the octree hierarchies and other hierarchies that you might want to use to accelerate collisions. Triangles are obviously triangles. Raycasts are obviously raycasts. But capsules are really, they're really good for things like humanoid-shaped objects, but that's about where it ends. And if your game doesn't feature a humanoid-shaped object, if your game features like chibi characters, then you might as well just use a sphere anyway. But we'll be getting to that in due time. I think next time I'm going to be looking at matrices again, and I'm going to be getting into perhaps the uglier side of matrices with multiplication and inverses and that sort of thing. And we're going to be using some of that when it comes to capsules. But that can wait for another day. My name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository down in the video description. Look for the 0.24 release, or the current branch would be like this branch, because I am attempting to use branches for this this project. If you want to contribute to the channel, links to a Patreon can be found in all the usual places. I would definitely appreciate it if you decided to pledge. I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Game, currently Bullet Hell. I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, KeyXE, Sindra Larson, Squarecrow, The Oz, and Zenith for supporting these videos. If you want to support the channel, head on over to the Patreon page down in the video description to join the fun.